Okay, so I paused for a minute. I had something going on. Let's get back to where we were. Well, let me just see here. I may start, maybe I'll just start here. Can't recall. Anyways, well, let me go back one more slide. It may be easier. So this is the formula. I was explaining this graph and the number of photons that are attenuated. So sometimes they use I instead of N, but either way, I or N is the number of photons that remain in the X-ray beam, the ones that are transmitted. N or I nod is the original amount, the original intensity. So I nod would always be 1 or 100%. Negative mu to the X is so mu is the linear coefficient and X is the distance that it's traveled through. So the higher the linear attenuation coefficient would mean the more dense or thicker the tissue, and it would result in a lower HVL, half value layer. Okay, so here's the same formula. It looks very similar to the activity formula, only instead of with activity talking about the photons that have been transmitted, with this formula, we're talking about the photons that have been attenuated. So I nod is the initial intensity before attenuation. I is the intensity after, when it reaches the tissue. What is the final intensity? And mu is the linear attenuation coefficient. It tells us how much attenuation has occurred over 1 centimeter. Okay, so mu, if they gave it to you in millimeters, we need to convert that to centimeters because that's the unit that we need. And E, whereas in the activity formula, it was 0.5. Well, in this formula, the linear attenuation coefficient formula, E happens to be a constant of 2.71. And it doesn't have any units. The reason why the linear attenuation coefficient is negative because it's indicating a decay, an exponential decay. So here's the two formulas just to take a look at them together. You have the activity half-life, which is how many half-lives an isotope has been, the activity has been reduced. So it looks at when the radioisotopes decays through a period of time. And that's the activity half-life problem. For an attenuation, then the linear attenuation coefficient tells us how much a photon beam intensity is reduced when it travels through a distance. So one tells us how it decays and how the activity has been reduced, and the other one tells us how much intensity from a photon has been reduced when it travels through a distance. So to figure out the half value layer, if you were given, let's say, the linear attenuation coefficient, then the formula is half value layer is 0.693 divided by mu. So we can just take this natural log of 2 and put in 0.693. If you're given the linear attenuation coefficient, then you would divide 0.693 divided by the linear attenuation coefficient, and we would get the half value layer. And remember, the half value layer is the amount of material used to attenuate the beam by exactly 1/2. So here in this problem, we were given the half value layer of 1.2. So it says the radiation emitted by a cobalt machine has a half value layer of 1.2 centimeters. I think it says in lead. What is the linear attenuation coefficient of lead for cobalt? So we were given the half value layer of 1.2. Okay, so half value layer. So the formula is here's half value layer equals 0.693. And we were given the we weren't given the linear attenuation coefficient, so that's that. That's the formula, so I can replace this. Have 1.2. So now we have 1.2 equals 0.693 by mu, and then I'll just multiply mu by both sides. And then I have mu times 1.2 equals 0.693. And so I'll go 0.693. I'm plugging it into my calculator, divided by 1.2. And I get 0.58 centimeters. Therefore, it took, that's how many centimeters of lead it would take. Okay, so that's that formula. So that was this part right here. The second part of that problem is B. So it said if a 5.05 centimeter thick block is fashioned from lead, what percent of cobalt will be transmitted through this block? So you have 5 centimeters thick block that's made out of lead. What percent of cobalt? Okay, so we already figured out from this last problem that the linear attenuation coefficient is 0.58. So we know that. And then it also told us that it's going through 5 cms of lead. Okay, so we can put that in our formula, which is I equals I nod times E to the negative mu x. Okay, so we don't know what we're trying to find out what the percent is transmitted, so we don't know that. We know we started out with 100%, or which is the same thing as 1. And then we know that E is 2.72. Okay, because that's just a given number. And then negative mu is 0.58. And x is 5. Okay. So I'm gonna go 0.58 negative times 5 is 2.9. So 2.79 to 2.9 negative equals 0.05. And so it's 0.05. I got 0.05 and then times 100, and that would be 5%. So that would be the answer there. So now this one says a certain material is used to construct a compensator for a 6 MV beam. It is noted that 79% of the beam transmits across 15 millimeters of this material. What is the linear attenuation coefficient? What is the material's half value layer? So let's see. So we started out with well, you're basically working backwards. So it's the finished attenuation is 0.79. Of course, we started with 100%. X, they told us, is 15 millimeters. So X always has to be in centimeters. So once we convert millimeters to centimeters, we get 1.5 centimeters. And then we need to find what the linear attenuation factor is. So once we take the natural log of everything, we can find it'll turn out to be 0.157 is the linear attenuation coefficient. And then if we wanted to find, what was the second part of the problem? Oh, what is the material's half-life? So here's the coefficient. The half-life we don't know. But we have the linear coefficient is right here. So half-life is 0.693 divided by 0.157. Let's see what that gives us. 0.693 divided by 0.157. And the half-life would be, I got 4.4. So here it is right here. So the half value layer is 4.4 centimeters. So 1.5 centimeters is actually less than 1/2 value layer, which makes sense since 71% has been transmitted. So 4% has been attenuated and 71% has been transmitted. So this is just showing you that, here's the question. There's a 75% chance that X-rays will be attenuated by 3 millimeters of lead. How many half value layers are required to achieve 75%? So if two half value layers is 3 millimeters, then each half value layer is 1.5 millimeters of lead. So they're saying the answer is 2 half value layers, because if you have 1 half value layer, then 50% is transmitted, 50% is attenuated. If you have 2 half value layers, 25% is transmitted and 75% is attenuated. And that's what they're asking you, 75%. So there's 2 half value layers. And if the half value layers are each 3 millimeters, they're saying if 3 millimeters is 2 half value layers, then each half value layer is 1.5 millimeters. Just divide 3 divided by 2. Okay, so now it says 8 millimeters of lead will allow for 6% of the beam to be transmitted. What is the half value layer? So here, well, this is just a table. This is saying 6% is transmitted. So it's 4 half value layers. And it says 8 millimeters of lead is 4 half value layers. So then each half value layer is 2 millimeters. So 2, 4, 6, 8. Okay, thank you, and I hope that was helpful.